Grocery costs vary for different families, but a researcher wants to study the weekly cost of groceries for typical Florida families at 4 different grocery chains in South Florida. To do this, the researcher looks at weekly costs for groceries at the 4 stores for 4 different families. Each family will visit a different one of the 4 stores to shop each week for a month. The families will randomly be assigned to the stores each week. Use the data below and a 2.5% significance level to test the claim that the 4 stores have different average grocery prices. So here we're going to test the claim that they have different average grocery prices. And we're told the stores, and we notice that the table looks like it's laid out in a 2-way format. So we have families, then the stores. And based on the description of the problem, it sounds like, of course, we're dealing with the classic scenario of a randomized block design. You notice that there's dependency among these columns because, for example, each of these numbers comes from the same family, family 1. So they're not independent columns of data. They're connected or linked by this family 1, family 2, family 3, family 4. So we're going to assume again here, it looks like they know that grocery costs vary for different families, right? So we're aware that the families' grocery costs vary, but we're interested in testing the claim that the 4 stores have different average grocery prices. So we don't really care that the families vary. We care about the different costs at the different stores. We want to see if there's truly a different cost for the different families depending on where they're going shopping. And so that's the idea of the problem, to focus on the stores and their prices and not so much the difference between the families. So we're going to try to block out the effect that the families introduce in the problem in order to focus our attention on what happens with stores. So it's randomized block design where the families are our blocks and the treatments are our different stores. Okay, so again, with all that, goes the assumption that there's no interaction effect, that there's no scenario where, let's say if Whole Foods proves to be the most expensive store in the list, we wouldn't want to see a scenario where, it turns out that it's the most expensive store except for when it's paired up with family 4, where it becomes, say, the cheapest store in their list. That would indicate that there's some sort of interaction between the families and the stores themselves, so that we don't have that consistent pattern where if this is the most expensive store, you see that for across all the families, it's the most expensive store, right? That's what we want to see. We want to see that there's no interaction. So it would be very strange if, for example, family 3, spends for whatever reason less at Whole Foods than any of the other stores, even though for every other family it's more expensive Whole Foods. That would indicate there's some interaction between the Whole Foods and family 3. But we don't see that in the data, and if we did a special plot, we'd be able to see that more visually. But basically we're going to assume that that's the case, that there is no interaction effect. All right, so from there, the next step is, after we're aware that it's randomized block design, and sometimes that takes a little bit to think through the problem to make sure, but here it's clear that it's randomized block design. Our next step then is to go ahead and come up with the claim that we have from the problem. So let's do that as our very next step. So this problem says, test the claim that the 4 stores have different average grocery prices. Different average grocery prices. Okay, so let's write that down first. So the claim is that they have different average prices. Okay, so I've abbreviated some of the words before this. But we're saying the claim is that the 4 stores have different average grocery prices. All right, let's get HO and HA from there. For the HO, we're basically saying that they're all the same. So the mean price for store 1, which I think was Publix, is equal to the mean price for store 2, which I believe in this case was Target. Let me just double check, so I don't remember actually. Yeah, Publix, Target, Costco, and Whole Foods. Okay, so Publix, then is Target. That'll be equal to the mean price for Costco, equal to the mean price for Whole Foods. All right, and then for HA, we're going to have a scenario where we say that at least one of these stores has significantly different prices. Okay, so I abbreviated it a little bit to fit it in the line, but it says at least one of the stores has significantly different prices. Okay, so at that point, the next step is going to be to manipulate the data and put it into this ANOVA table. So let's draw the ANOVA table as we've done in the past. So we'll create a box here that we'll fill in the ANOVA table into. And we're going to have the sources of variation. We'll have a column for that. We'll have a column for the degrees of freedom. We'll have a column for the sum of squares, a column for the mean squares, and lastly, a column for the test statistic F. So sources of variation, degrees of freedom, sum of squares, mean square, and F. All right, and then for the sources, we're going to have treatments. So we'll have variation due to the treatments. That'll be the stores in this case. We'll have variation due to the blocks. In this case, it'll be the different families of the blocks. Then variation due to the random error that's present. And then, of course, we'll have the row that we put the totals in, right? All right. All right, so the rest of this we'll fill in after we come back from the step where we work the data. So let's actually go ahead and go to that step where we take all the data from our problem and manipulate it so we can fill in the ANOVA part of the table. Okay, so the first part of the data step that we'll work out is the correction factor, the CF, the correction factor. Now that's going to be the summation of the yi values, which are the response variables, basically, squared, divided by the number of values total in the table. So we're lucky enough to have this value provided to us. It's 3,471. So 3,471, which we'll square and then divide by n, which is the number of total values in the table here. So it looks like we have 1, 2, 3, 4 columns of 4 values, so we'll have 16 total values there. Let's work out the correction factor, see what that gives us. All right, so when we do that, we end up with the answer 3471 quantity squared divided by 16. And we get the answer, it's kind of a large number, it's 75,000 or 752,990 basically. I'm going to store that in my calculator as x so I can just use it over and over again without having to type it in. But the answer turns out to be 752,990.0625. So kind of a large correction factor compared to what we normally get. But this is because the values here that we're working with are pretty large since they're grocery total amounts, right? The dollar amount spent on groceries each week. All right, so let's now go on to the next step, which is to come up with the sum of squares total, or the total sum of squares, SS total. Luckily, that's been done for us, so we don't have to do all the work that's required. It's the same work we did in the previous, by the way, completely randomized design problems. If you want to get the sum of square total, you actually square each and every single value in the table. That takes a lot of work, right? Once you square them all, you add them all up, and you divide by the number of values you have. You don't divide by the number of values, pardon me. You square all these values, you add them all up, and then you subtract off the correction factor that we calculated in this other part of the problem. So either way, it ends up giving us 83,328.9375. So that's your sum of squares total. All right, next step is to get SST, which is the sum of squares for treatment. Now, basically, you remember how to do this. We have to take the total for each column here, the treatment total, and we're going to square it and divide by the number of values in the column. I've come up with the totals already for us. I wrote them in red, so we would have them. So the total for the first one is 834. We're going to square that and divide by 4 because there are 4 values. There are also 4 blocks. Remember, this number is the same as the block total, right? Or the number of blocks, pardon me. And then we have 743 squared divided by 4. Then we have 794 squared divided by 4. And then the total for this column is 1100. So 1100 squared divided by 4 minus the correction factor. All right, so let's see what that gives us. So we're going to end up with 834 squared divided by 4 plus 743 squared divided by 4 plus 794 squared divided by 4 plus 1100 squared divided by 4. And all that minus our correction factor, which I programmed in my calculator, stored in my calculator under X. Okay, so we work that out, we get 19,020.1875. So 19,020.1875. 1875. Okay, so that's our correction factor. Sorry, not our correction factor, our sum of squares for treatment. So we've got our sum of square for total, our sum of square for treatment. Next step is to get sum of square for blocks. So sum of squares for blocks. Sum of squares for blocks is basically just like the sum of squares for treatment, but now we work in the blocks, right? So the blocks are the families here. And what we're going to do is we're going to square each of these values and divide by the number of values in the row. That'll be the same as the number of treatments, or 4. So we're going to have 920 squared divided by 4 plus 1,225 squared divided by 4 plus 759 squared divided by 4 plus 567 squared divided by 4 minus the correction factor. Okay, so it's going to be a very large set of numbers when we square these values, but it's okay because we're going to do them all at once. So 920 squared divided by 4 plus 1225 squared divided by 4 plus 759 squared divided by 4 plus 567 squared divided by 4, and of course minus our correction factor, which I again have stored in my calculator already as x. And when I work that out, I get 58,158. So 58,158 point, and then we have 6875. 6875. Okay, so again, that's our sum of squares for blocks. All right, and the last sum of squares we have to get in this problem is the sum of squares for error. Sum of squares for error. So to get the sum of square for error, we have a nice simple subtraction problem to work out. It's the sum of squares for total, or the total sum of squares, minus the sum of squares for treatment, minus the sum of squares for blocks, and this will give us our answer. So we subtract these things, and again, we've discussed this before, because our model is essentially that all the variation in the problem is due to 3 sources here: the treatment effect, the block effect, and the random error. So if we take away the treatment and the block from the total, we'll be left with just the random error. So that's our idea. So sum of squares for total is a large value. It's 83,328.9375. We'll subtract off from that the treatment value, which is 19,020.1875. And then finally minus the 58,000 we had for blocks, 158.6875. All right, let's put all that in our calculator and figure out finally what our sum of square for error is. And so we have 83,328.9375 minus 19,020.1875 minus 58,158.685. Okay, when we work out all that, we get 6,150. So 6,150.0625. 0625. Okay, so there it is, the sum of square for error. We have our sum of square for blocks, sum of square for treatment, sum of square total. All right, let's take those values now and plug them into our ANOVA table and see what our final conclusion is after running our hypothesis test. Okay, so let's fill in our table now. So we can see here that the treatments, there are 4 treatments. Remember, Publix, Target, Costco, Whole Foods. So we'll take away 1 to get the degrees of freedom for treatments as 3. The blocks, when we look over here, we see that there were actually 4 treatments and 4 blocks. Remember, the denominator of the sum of square treatment fractions here, the denominator is the same as the number of blocks. So if we take 1 away from that, we'll have the degrees of freedom for blocks. Now for the error, we're going to get that by subtraction, so we're going to go after the one for total first. So let's look at degrees of freedom for total. The total number of values was 16. If we take 1 away from that, we get 15. All right, and then you have 6 here. You subtract that from 15, you end up with 9 for the error term. All right, the sum of squares for treatment, we work that out. It's over here. It's 19,020.1875. So let's just say 188 to squeeze it in the table here. For the sum of squares for blocks, we're going to have 58,158.688. For the error, the sum of squares for error was 6,150.063. And then, of course, sum of squares for total, we don't actually need this value, but we can plug it in. It's 83,328.94, let's say. We don't need that in our calculations as much, but since we have it in the beginning to get the rest of these values, we'll put it here anyways. All right, MS now, the mean square, is going to come from dividing the degrees of freedom into the sum of squares for each of these top three here. Okay, so again, we don't need to fill in this, we don't need to fill in this, we don't need to fill in this, right? The bottom three we can leave out. Got to get the two F statistics and all these MS values. Okay, so let's get MST first. In order to calculate MST, we're going to simply do the 19,020.188 divided by 3. And we get the answer 6,340. So 6,340.063, let's say, 063. All right, we're going to do the same for the 58,158.688. We're going to divide that by 3. And we get the answer 19,386.229. 229. All right, and we'll do the same here for 6,150.063. This time dividing it by 9, the degrees of freedom there. We get 683.340. All right, and remember, now from here we have to divide the error into the treatments to get MS. Sorry, well, let's do it here first. To get the F value, which is going to be MST over MSE, right? And then we'll do the same thing. We'll do this guy into this guy, the errors into the blocks to get MSB over MSE, which of course is our F statistic for our block value. Okay, so we can calculate this test statistic here, but we don't actually usually run the test upon that. We could, but we don't have to unless we're interested in it. So 19,386.229 divided by 683.340. So we do this one, the 683 into the 19,000, we get the answer 28.370. 370. So it looks like that's probably going to be significant. So the blocks look significant, so probably we would find that in the rejection region, which means that it was a good idea to separate the families out and block out their differences, because they do have some differences there. Now let's talk about this guy. So error into the treatments is going to give us 6,340.063 divided by 683.340. And when we're done with that, we get the answer 9.278. 9.278. So let's compare that test statistic for the treatments, which is for the grocery stores. Let's compare that test statistic against a critical value. So we're going to go to our table and determine that. So before we do that, let's go ahead and set up the critical region. To set up the critical region, we're going to draw the F curve and then determine the numerator degrees of freedom, the denominator degrees of freedom, and so on and so forth. So let's do that here quickly. Just place this over here and let's draw our F curve for a minute. So our F curve, again, looks like a right skewed distribution with a tail here. That's going to be our rejection region. Starts here at 0. And we're trying to determine where the critical F value is on the number line. We want to know what number it is. So we're going to use our alpha. If you look back at the problem, it was 2.5%. So 0.025 was the alpha. And then we had numerator degrees of freedom. So what was the degrees of freedom for the MST value? It was 3, right? And then the denominator degrees of freedom, the MSE value, so that was 9. So that's what we're going to go to our table and look up. We're going to look up degrees of freedom 3, degrees of freedom 9 on the 0.025 table. And remember that 3 is your numerator degrees of freedom, 9 is your denominator degrees of freedom, and look it up on the 0.025 table. So let's go there now and get our critical value. Okay, so we're on the F table, the 0.025 F table, and we're looking for numerator degrees of freedom 3 and denominator degrees of freedom 9, and we find the answer 5.08. Okay, so we found our critical value to be 5.0781. Now looking at our F test statistic for treatments, we found it to be 9.278. So that's clearly in the reject HO region. So we're going to decide to reject the null hypothesis, therefore support the alternative hypothesis. And looking back at our claim, it said, basically that the stores had different average prices, which is the idea behind HA. So we're going to say the sample data support the claim. The sample data supports the claim. Supports the claim. And of course, the claim is that the 3 or 4 different grocery stores have different average prices for the groceries.